So I wanted to show you how to write a solution when you have complex eigenvalues. Because this isn't just a 17b thing. We end up, what's very strange is imaginary numbers, what you learned, probably did a unit on in a previous math class. And I remember teaching that. And, you know, when with high school level math, you know, there isn't really much you could apply that to, because the typical question is, why are we even bothering studying imaginary numbers if they're not real, if they're just a figure of our imagination? Well, the truth is, even though they aren't real, they end up being a good model. If we study imaginary numbers, they can correctly model certain dynamics, namely for us, for our purposes, what we're studying now is iterated matrices, right? The example I want you to always think of, and I'll always think of, is the, what was the one we did last time? The squirrel population, right? With different age classes like adolescents and adults, and how does the population change over and over and over each generation if you assume certain characteristics like survival rates and offspring numbers. So that's the idea. Okay, but before we just jump into it, I was watching the class lecture and it occurred to me that I don't know how much experience people have with complex numbers, given that math has changed. Math education has changed in the last few years. So we'll review that. Something you did cover in Professor Burke's class, but I, for lack of time, didn't really mention this too much, is the idea of a rotation matrix, because that's comes up in this section. What a rotation matrix is remember when we talked about eigenvalues and eigenvectors, and the whole key thing of an eigenvalue and an eigenvector is it gives you the ability to multiply a matrix times a vector, and it will just change the length of the vector. It will not change the direction. Well, another thing that can happen is you can multiply a matrix times a vector, and it will just rotate the vector, but preserve the magnitude. I know I did a couple examples, but I don't know if I actually identified it as a rotation matrix. And how they can be developed is, if you want to rotate a vector by an angle theta counterclockwise, then the matrix is cosine theta, negative sine theta, cosine theta, and it will, when applied to any vector, rotate it by a certain angle. For example, the rotation matrix for pi over 3 would be the cosine of pi over 3, negative sine pi over 3, sine pi over 3, cosine pi over 3. Okay, and so there's a little bit of trig here, right? If you want to find the cosine of pi over 3, some of you, I've taught this before. If you use your left hand, this is 0, pi over 6, pi over 4, pi over 3, pi over 2. Those are all the special angles in the first quadrant. If you want to find the cosine or sine of pi over 3, you find the correct finger. 0, pi over 6, pi over 4, pi over 3. So pi over 3 is right here. If you put that one down, the cosine of pi over 3 is the square root of 1. I have one finger above. The square root of 1 over 2, which is 1/2. The sine of pi over 3 is the square root of the fingers below, square root of 3 over 2, root 3 over 2, I should say. So this becomes 1 over 2, negative root 3 over 2, root 3 over 2, 1/2. Okay. Or use the unit circle or whatever, or the triangles, whatever you use to find those values. Has anybody seen that finger trick for finding sine and cosine? It's a pretty cool trick that, no, you haven't. Okay. Oh, I might have to show it. Yeah. Maybe I need to make maybe I'll make a special, a little video on that just because it seems like there's angles involved when we're doing these. So anyhow, because that's not the big point here. If I take this matrix and multiply it by this vector right here. So if I multiply, so I'm going to do r of pi over 3 times this vector root 3 over 2, 1/2. So that's 1/2 negative root 3 over 2, root 3 over 2, 1/2 times this vector root 3 over 2, 1/2. You end up getting, whoops, move that up a little bit. That's going to be root 3 over 4 minus root 3 over 4. So I end up getting 0 for my x component. Root 3 over 2 times root 3 over 2 is 3/4 plus 1/4 gives me 1. And you really need to see what just happened here to appreciate this. So let me draw some axes here. And let me move that up. So this first vector right here, let's call this vector v, not v1, just vector v. Root 3 over 2, 1/2 is a vector that goes root 3 over 2 plus 1/2. And you may recognize those as values of sine and cosine. It turns out that this vector makes an angle of pi over 6 with the x-axis. This is vector v. I keep putting v1, vector v. When I multiplied, which is 30 degrees, 30 degrees. When we multiplied this vector by this rotation matrix, we ended up with the vector 0, 1, which is a vector that's pointing straight up. This is a times v, is this vector right here. And that is exactly right. If this is 30 degrees, then one way to describe what just happened is it just rotated this vector counterclockwise by 60 degrees, which is pi over 3. So that's what we mean by a rotation matrix, is when you multiply that matrix by a vector, it essentially just rotates the vector by whatever angle you put in for your cosine and sine, counterclockwise. It wasn't just this vector. Any vector would do that. I just chose this vector so we could clearly see that. Okay. Okay, so keep that in mind because that shows up later on in this discussion. I have another example, but I realize I'm going to be short on time if I don't, because we need to get to the meat of this. Complex numbers. It's been a while. A complex number is otherwise known as imaginary numbers, but complex is a little more complete in that a number like the square root of 3 plus I has both a real part and an imaginary part. That's considered a complex number. So if we wrote it as a plus b times I, a is the real part, b is the imaginary part. And one way to represent a complex number, since we write it kind of differently than a regular number, is with a vector, actually. So we can graph a complex number like the square root of 3 plus I by thinking of the x-axis as the real part of the number and the y-axis as the imaginary part. So the square root of 3 plus I would be plotted. I would go over square root of 3 on the real part and then go up 1 unit, because you can think of this as, so like for my example right here, a has a value of root 3, b has a value of 1, right? You can imagine a 1 in front of the I. So I go over root 3, up 1, and that point in the complex plane is how we describe this. You would make a vector from the origin that takes you to that point. And so this vector represents this complex number. And we know since vectors have both magnitude and direction, the magnitude of my vector, as we know, is just the square root of each part squared. It's just a Pythagorean theorem. So in general, the magnitude of r is the square root of a squared plus b squared. And the angle that it makes with the x-axis, you would have a and b, so you would use the tangent function. The tangent of theta is b over a, which means theta could be expressed as the inverse tangent of b over a. So in our problem, for us, the magnitude of r is the square root of root 3 squared plus 1 squared, which is the square root of 4, which is 2. And theta is the inverse tangent of b over a, of 1 over root 3. Yeah, here you might need a little knowledge of the unit circle or triangles or whatever, but this angle ends up being pi over 6. Okay, so that's a complex number. And then as you saw, if you watch the notes on this, the videos, there's a special theorem that we use if you want to raise a complex number to a power. We use probably French, de Moivre's theorem. I'm not sure exactly how to pronounce it. De Moivre's theorem, which says if you take a complex number to some power t, interestingly enough, cosine and sine become involved. There's a way to show this, but it's not within what we've learned in the 17 series. But it's basically r to the t. And what I wanted to note here, what they really mean by r when they give you this formula, they mean the magnitude of r, the magnitude of r. It's the length of vector r. Raised to that power times the cosine of theta t plus I times the sine of theta t times t. And I'm kind of curious because I've taught several high school algebra 2, what they used to call it, pre-calculus courses in my day, and not always have I seen this theorem mentioned. How many people remember this theorem, or not that you know how to use it, but you remember learning this in a previous high school class, most likely? Okay, I see yes, I see no. No, okay. No, right? Yeah, I suspect with the new revamping of the math curriculum that it's maybe not emphasized as much anymore, and perhaps rightly so. It's a pretty specific theorem, and I can totally see if they were going to cut stuff out, this might be the thing to cut out. So yeah, when I was watching the module videos, I was like, I'm not sure everybody's going to remember that theorem or even be familiar with it. So I thought I'd introduce it. Okay, so for example, this is one kind of use for this. Say you wanted to take root 3 plus I and raise it to the 6th power. Right? Now, one way to do it is you can do this just like you would if you were doing x plus y to the 6th power. You could FOIL out root 3 plus I times root 3 plus I all the way out 6 times if you really want to. Okay, I don't think I'd want to do that. But if we use de Moivre's theorem, or use, how about I put Diem's theorem, this is going to equal r to the t, or the magnitude of r, which we have right up here, 2. So it's going to be 2 to the 6th times the cosine of theta. Now, theta we found was pi over 6 times t, which is also 6, plus I times the sine of pi over 6 times 6. 2 to the 6 happens to be 64. This just becomes the cosine of pi plus I times the sine of pi. And these are easier if if you think about the graphs of sine and cosine. The sine of pi is 0. And this sine of cosine of pi is -1. So this just ends up being -64. So if you were to have the time and energy to multiply out √3 plus I times itself 6 times, what you would see is a bunch of stuff canceling out for one thing, and eventually you would end up with the answer -64. So it is kind of cool, I think. But how many times in your life are you going to be multiplying out a complex number to a power? Well, strangely enough, we will be here. Okay, so all of that was sort of background information to help us with, this is number 31 in section 8.8. I think it was one of your recommended problems, which I don't think she did in class. And I could have chosen to do another one, but this one just works out nice. So I'm going to do this one. So let's say we want to find the solution to a recursive situation. Okay, so have the squirrels back in mind, right? Like a Leslie matrix that's defining the population of squirrels over time. And we're trying to figure out what's going to happen long term. If A is my matrix that has all of my dynamics, and this is my initial population size. Remember, we could think of one as like the population size of juveniles and this one of adults. And we want to see what happens with these dynamics going on with this population. And from last time, we decided that even though there were 2 ways to solve for the population over a long period of time, one with the diagonal matrix and the P inverse, we decided this one was better. All right, so your solution for the population at any time t is going to be taking this matrix to the t power times your initial population size. And we know the formula for that is C1 lambda 1 to the t times its eigenvector plus C2 lambda 2 to the t times its eigenvector. So step number 1, let's find our eigenvalues. And we know, take the short road here, it's going to end up being the determinant of your main diagonal minus lambda, off diagonals stay the same, set equal to 0. And this, to find this determinant, we multiply these two together. So that gives me 1 minus lambda times 1 minus lambda. I'll write that as 1 minus lambda squared minus the product of the off diagonal, which is -1, and set this equal to 0. We could FOIL this out, but since this is squared, here's what I'm suggesting is let's just, this is +1. So if I move it over to the other side, this would equal -1. And I can solve this faster, I think, by just taking the square root of both sides, remembering that when I solve an equation by taking the square root, I have to remember to do plus or minus on one side or the other to get both answers. So I end up with 1 minus lambda equals plus or minus the square root of -1, which we know is plus or minus I. And so if I it's a little weird, but if I like add my lambda over here and either subtract or add I over to this side, it's not going to matter. Do you see that you're going to get 1 lambda equals 1 plus or minus I? Now, for purposes of what we're going to be doing with eigenvalues, both this quarter with complex eigenvalues, both this quarter and in 17C, I didn't hear this mentioned in the video. I don't know, not sure why, but it turns out we only need to work with one of the eigenvalues and eigenvectors, only need to work with one of the lambdas and its vector, its eigenvector. And the reason this happens is if you find the eigenvalue and the eigenvector for the second one, and then you write the solution, it turns out that they can be combined into one anyhow. How do I put this? Because if we use both, they could be combined. There we go. Into one solution anyway. I don't know if that makes any sense. I can give a more detailed explanation, perhaps in 17C, for why that's true. So we really just need to one. So I'm going to choose just randomly. Probably I might as well, because I want to think positive here. Therefore, we're going to choose to work with 1 plus I rather than 1 minus I. We could have chosen either one and it would, no, it doesn't. Yeah, I see that in there. It doesn't really matter. So, but we do need the eigenvector for that. So to find my eigenvector, remember to find E vector, we're using A times my vector equals my eigenvalue times my vector. Well, there's no point in really numbering it because it doesn't really matter, but I guess I will anyhow. We'll just do that because we're only using one anyhow. So I would take my matrix 1, -1, 1, 1 times my vector, which is to be determined x, y. It always looks a little weird when you're working with these imaginary numbers, but it works out okay. So if I multiply out the first row times this vector equals the top number, I end up getting x minus y equals 1 plus I times x. And remember what we've said, I know in class, I just saw it, she writes out both of them and just tells you can choose which one. I just might as well just go with the first one and not worry about the second one unless I get stuck here. So I'm going to proceed with this. I'm going to distribute this. And that gives me x minus y equals x plus I x. These two x's cancel out. So if I solve for y, I end up getting y equals negative I times x. And I can use that. So with that information, what I would do is choose x to be 1. And I get my vector. If x is 1, then y will be negative I times 1, which is negative I. Okay, I ended up with a negative anyhow. Okay, so then to write the solution to this, because, okay, let me, well, do you have that? Can I move that up? Okay, if not, I can put it back up. I probably should have asked this first, because what I'm saying is to write the general solution, because we only need to work with one of the lambdas, you know how we had normally it's C1, lambda 1t, V1 plus C2. We really just need to work with one of them. And so it's really just C lambda 1 to the t times V1. which means it's really some constant c, 1 plus I to the t times this vector that we just found, 1 negative I. But what we want to do is we want to use de Moivre's theorem to rewrite this, right? To use that and rewrite this in terms of cosine and sine. So that's why I'm asking this up here. I can maybe squeeze them both in. We want to be able to rewrite 1 plus I to the t using de Moivre's theorem. And so remember how we can do that. What you could do is plot 1 plus I. There's formulas, but I see it more visually. First, plot what 1 plus I would look like on the real and imaginary axis. Here, A would be 1, B would be 1, right? So that would be a vector that goes over 1, up 1. 1, 1. So this would be my vector. If I thought of this as a vector, this would be R is 1 plus I. And what we saw with de Moivre's theorem is it said that 1 plus I to some power would be, really it's the magnitude of R, as I said, raised to the t times cosine of theta t plus I sine of theta t. This is too far away. So we need to find the magnitude of R. That's easy. That's just the square root of 1 squared plus 1 squared, which is root 2. And we need to find our angle theta, which is the inverse tangent of 1 over 1. Or you may know that. What's that angle? That's 1 over 1. If this is root 2, we already found that's root 2. You should be able to see that that angle is pi over 4. And so using this information, then I know that 1 plus I to the t is the same thing as root 2 now to the t times the cosine of theta t. So pi over 4t, I guess I'll put little parentheses around that, plus I times the sine of pi over 4t. And this is what I was looking for, because now I can replace this part right here. I can't see that. Could get replaced with this. So I would end up with C times root 2 to the t plus I, put an I in there, sorry, I sine of pi over 4t times the vector 1 negative I. Now, all of this, there's really two answers here, right? Because remember, we're supposed to be ending up with a vector, two things here. So one of it is all of this times 1, and the other one is all of this times negative I. So I'm going to just keep these two out. So I have C times root 2 to the t, but then I'm going to turn this into like a matrix or a vector where I have this times 1 So that gives me cosine pi over 4t plus I sine pi over 4t. And then the bottom row, this is where it gets a little tricky. It's this times negative I. So I would end up with negative I times cosine pi over 4t. Okay, you ready? This negative I times this I would make this minus I squared times sine of pi over 4t. What do we know I squared equals, though? It's our definition. I squared equals. Well, the whole thing will be 1. Yeah. I squared itself equals, remember, I squared is the square root of negative 1 times the square root of negative 1. So I squared equals negative 1. So this part right here is negative 1. But then, of course, if there's another negative in front, this whole thing's just going to turn into positive 1. So all of this just turns into plus 1 because I have negative of negative 1. Okay, a little more rearranging here. Now what I'm going to do is I'm going to separate out the real parts of each solution, each row. So the real part here, I have cosine of pi over 4t. What's the real part in the bottom row? It's now this term, right? Because this term now is just positive 1 sine of pi over 4t. I'm just going to emphasize here, this is the real part. And then, of course, I'm going to take the imaginary part. And how you're going to know it's imaginary, which is this term and this term, is I'm going to take out an I. So you know it's imaginary. If I factor out an I from this term, that'll be sine of pi over 4t. If I take out an I from this bottom term, it will be negative cosine pi over 4t. We're almost there. Hey, you didn't think writing the solution with complex eigenvalues would be easy, right? It's going to be complex, of course. But we're almost there. We're almost there. Now, this is a little bit of waving a magic wand here, but that's okay. Here's what we're going to do. If I take this constant and distribute it, okay, right here, you could, if you had to put something there, you could think there's just a 1 there, right? If I distribute this, C times 1 is just C. It's just a constant. But C times I, I'm going to pretend that's a different constant. So if I distribute this, here's what I get. I get root 2 to the t, parentheses. C times 1, I'm going to call that C1 now. Cosine pi over 4t sine pi over 4t. But C times I, I'm going to replace that with a different constant. I'm going to call that C2 sine. Let me make a note of that because that is a little bit weird. So I'm calling C times I, I'm calling this C2. That might bother you a little bit in some way that you're taking a constant times the square root of negative 1 and claiming it's just another constant. I guess it's an imaginary constant, but who knows, right? We'll just go with it. Okay. So this is our general solution right now. This is n sub t. Remember, that's always the goal in this section, is to find a formula for your population at some period of time. But that's our general solution. We need to find our exact solution, which goes back, if you look back at the problem statement, it had an initial condition of n naught equals 1, 1. So if I set 1, 1, and initial condition means you're plugging in t equals 0, right? This means t is equal to 0. So root 2 to the 0 is going to just be 1. And then this is going to turn out to be the cosine of 0, because t is 0, the sine of 0. This will be the sine of 0, and this will be negative cosine of 0. And this is just equal to 1. So if you read the top lines here, what you end up with is 1 equals C1. Cosine of 0 is 1. Here, you know what? Let me take one more step here. Let's just do this. I don't want to. Cosine of 0 is 1. Sine of 0 is 0. So that's 0, and this would end up being negative 1. So there's two equations here. 1 equals the top row, C1 times 1 plus C2 times 0. So that tells me C1 is equal to 1. The bottom row tells me 1 equals C1 times 0 plus C2 times negative 1, so minus C2. So then I know C2 is equal to negative 1. And then I just go right back and put those into my general solution that we wrote a few lines above here. Put those two constants in there, and we're going to have our general solution. One times cosine pi over 4t minus 1, because C2 is negative 1. And if we put this, we could combine this into a single matrix. If we want to get the answer that they have in the back of the book, this is totally fine, but if we want to get that answer, we would write it like this: root t to the t, root 2 to the t, and then times, I'm going to make this one single matrix where my top matrix is cosine pi over 4t minus sine pi over 4t, sine pi over 4t, negative negative makes this plus. Now, the problem ends there. How much time I got? Perfect. I got 5 minutes. The problem ends there. But I think the book's missing out on a really important observation about what's going on here. Take a look at that matrix and tell me what special kind of matrix does that remind you of that we discussed earlier? I don't know if hopefully I have a page still. If you're still with me. What matrix has like sines and cosines in it? I know I only gave you one example. I think she did 1 or 2 in her lessons, but yeah, how many people see that is a direct, exact, right? Cosine, cosine, there's a negative sign, positive sign. This is in fact a rotation matrix. And so what's going on? What does this do? Is rotating it pi over 4 times t, whatever t. Remember, t would be like a time period, right? Like when t equals 1, t equals 2, that's like what's happening to your juvenile and adult population. This is a rotation matrix that is moving my vectors counterclockwise. This is a rotation matrix that moves each successive vector counterclockwise by pi over 4, really pi over 4 times t, whatever t is, assuming t is incrementing by 1, then it's going to move it by counterclockwise by pi over 4. Let's just do that. When I say successive, what I mean is t is 0, 1, 2, 3, right? You're not like plugging in 1.5 or something like that, or skipping numbers. It's moving it counterclockwise. Now, there's a really important, especially for next quarter, implication of that, of what's going on. We actually could have seen this at the very beginning. Oh, okay, this was just restating what I just said. So successive solutions produce vectors that rotate counterclockwise by theta equals pi over 4. Okay, I said it twice. Okay, remember the original problem statement gave this matrix and this initial population size or initial condition. And essentially what we're trying to find is what's happening over time, right? If we take this population and keep applying that matrix to it. Well, let's try that a few times and we're going to actually see exactly what our solution is predicting would happen. If I take this original matrix, this was our original matrix A, and this was our initial condition, let's see what we get. We get 1 minus 1, I end up getting 0, 1 plus 1, which is 2. Let me calculate all of these first, and then I want you to see what's happening. If I then take this population n1, multiply it by my matrix again, 0, negative 2, 0, 2, I get another vector. Take that, let's do it one more time. Negative 2, negative 2, negative 2, positive 2. Okay. So what I want you to see, let's plot these vectors on the, now we're on, these are real vectors. This is not imaginary real. This is real vectors, real numbers here. So if I took my initial vector, which was the vector 1, 1, that vector might look like this. Here was n naught, which was 1, 1. When I multiplied my matrix by n naught, I got this new vector 0, 2. That vector is a vector that points straight up 2 units long. So it's a little bit longer than this one because this one had a. So here's n2. No, n1, sorry, that's n1. n2 is negative 2, positive 2. So that's negative 2 units, positive 2. It's a little bit longer than this one. Here's n2. And n3 is negative 4, 0, which is just a vector going in the negative x direction. Here's n3. And hopefully you can see 1, 1 makes an angle here of pi over 4, right? That's 45 degrees. The angle between this one and this one is pi over 4. The angle between this one and this one is pi over 4, pi over 4. So what's happening is exactly what we found out when we did the solution. Once we recognized it was a rotation matrix, is as we multiply our matrix by these vectors successively, we're getting vectors that they are getting bigger in length, but they are rotating counterclockwise by an angle of pi over 4, which is exactly what we were seeing with our solution, right? Which means, okay, this is the complex numbers, which involve imaginary numbers, which are a figment of our imagination. They're not even real, but we can still use them to correctly model exactly what's happening, right? Exactly what's happening. In class, I did see her refer to this in either in class or in the video. If you think about the population over time as like points, because remember, this is like remember, this could be interpreted as your juvenile population if we were talking about squirrels, and the other number could be referring to your adult population. We could also be referring to this in 17C. We're going to apply this to predator-prey models. So this might be your prey population, your predator population. If you think of these as a bunch of points, what you can kind of imagine, I could just draw this right here. Population here, 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 is a spiraling population that's getting bigger and bigger and spiraling outward, which is, if you think about like if the x-axis represented, let me switch it to like your prey population, and the y-axis represented your predator population, predator. As you move around the circle, notice your prey population is decreasing. And once your prey population decreases, what happens to your predator population? It decreases too, huh? But as your predator population decreases, now your prey population is getting bigger because your X is getting bigger. And as that happens, your predator population starts to get bigger. So what the last note I wanted to say on this, the solutions trace out a spiral that gets bigger by a factor of root 2 each iteration. And this type of solution often, in fact, we will do this in 17C, describes predator-prey dynamics, that kind of spiraling. Inverse relationship, perfect. That's a very good way to put it. As one gets bigger, the other one gets smaller. Now, obviously, we just spent the whole period and then some doing one problem. But what I could certainly imagine happening as a possible test question, I mean, some of what took time was computing the eigenvalue and the associated eigenvector. Suppose that was provided for you and you just had to pick it up from there. Then I think it's a reasonable problem, right? So I wouldn't dismiss this as a testable question just because it's long. It could be made shorter. So, all right. But that did take longer than I anticipated. I better stop here.